So I just told you that yesterday we talked about the order of reaction, like why is there 0, why is there 1, why is there order 2. And I told you that the rate of the reaction depends on the slow step. Just a quick recap of what we were doing. So what order 0 meant was, what did it mean? It meant that the rate simply isn't dependent on the concentration of the reactant. 1 meant that the rate had a linear relationship, which is that if you change the concentration, the speed of the reaction would also change accordingly. The third one was that if you change the concentration, it's a quadratic relationship. The rate is very sensitive to the concentration of X. You double it, it becomes quadrupled. If you triple it, it becomes 9 times. If you make it half, it becomes 1/4. So I explained that it all depends on the mechanism of the reaction, what's going on and how many steps are involved in the reaction. Most reactions are not as simple as the equation that we study. Okay, you studied in organic that a lot of reactions have multiple steps. So the rate of reaction never depends on the slow step or anything in the slow. Sorry, it depends on the slow step. It doesn't depend on the fast step. Anything that's in the fast step, any reactant that's in the fast step, if you change the concentration, the fast step, no matter how fast it becomes, you increase the concentration of OH ions by 1,000,000 times and the collisions increase and the fast step becomes even faster. The overall speed of the reaction hardly changes. I mean, it goes from 101 seconds. You speed up the fast step, it goes from 101 seconds to 100.001 seconds. So barely any difference, any noticeable difference. So the point is that it's pointless to increase the concentration of OH ions. It's not going to affect the rate of the reaction. The rate of the reaction is only affected by anything that's present in the slow step. You speed up the slow step, you increase the concentration of the reactant, you double the concentration, the collisions double, the reaction speeds up, and obviously there's going to be a drastic change in the speed now. From 101 seconds, it's now all of a sudden dropped to 51 seconds. So that's fast. So we discussed this and we talked about order 2 yesterday. How are reactions order 2? So for example, and I'm going to give you some other example now. Let's say you have this reaction. I'm just going to make a mechanism myself. Okay, let's talk about a random mechanism. I've got okay, so this is just an example of order 2. So I've got this reaction where NO is reacting with, let's say, Br2, 2NO, and they react together to form 2NOBr. Now there are 2 reactants involved. There's Br2, and at the same time there's NO as well. So you have 2 reactants that are involved. Except that the reaction is not that simple, that there's a mechanism going on. What happens is, in step 1 of the reaction, what happens is that NO first initially reacts with the Br2. And what it does is that it produces NOBr, and one of the Br remains. And in the second step, that Br, that leftover Br, reacts with the other NO and forms NOBr again. So that's how you get 2 NOBrs. And anyway, so that's step 2. So I told you that the rate of the reaction depends on the slow step. So let's assume that the second one is the slow step. So that means, and the first one is the fast step. So the first one is kind of irrelevant, shouldn't affect the rate of the reaction. The rate of the reaction would be dependent on the reactants that are involved in the slow step, which in this case is Br and NO. Right? So that's your slow step. A rate should depend on this slow step. Now, so now the thing is, rate should depend on this slow step. Now the thing is, I said, just hold on just a minute for the azan. चले ठीक है. Let's get back to this. ठीक है. I'm gonna answer both questions. Just I'll give you examples of both. ठीक है. So right now, let's assume that the second one is the slow step and the first one is the fast step. ठीक है. So I'm going to do it both ways. So you'll get two questions. Either this would be given and you'll be able you will be asked to find the order of the reaction, or the reverse, that the order of the reaction would be given and you would be asked to figure out the slow and the fast step. So just 1 second. So let's assume that step 2 is the slow step. So rate depends on the slow step. So rate depends on NO and BR. So now the thing is, yesterday we did discuss about intermediates. I told you that when I say that rate depends on BR and NO, if you look over here and if you focus on BR, BR is not your reactant. I mean, BR2 is your reactant, but not BR. BR was made in the previous step. And BR's concentration depends on the concentration of these two things. Because if the concentration of NO and BR2 is high, then the concentration of BR would also be high. So when I say that rate depends on my slow step, it depends on the concentration of BR and NO. This BR is made in the previous step, and this BR itself is dependent on the concentration of NO and BR2. So instead, when I said that rate depended on BR, it actually indirectly depended, or it indirectly did not depend on BR, it actually indirectly depended on NO and BR2 because they were making BR. So when I say rate depends on BR, it actually depends on NO and BR2. So they would come into the expression. And if you sum this up, this becomes, NO comes in twice, so it's going to become NO squared. And BR2 is only appearing once. So that means with respect to NO, the order is 2. That means the rate would be very sensitive to the concentration of NO. It will have a linear relationship with BR2, but not with NO. And I'm going to explain how that's going to happen. That if you change the concentration of NO, what happens? If you change the concentration of NO, what happens to the slow step? Now, if you change the concentration of NO, then the slow step would speed up, right? But if you change the concentration of NO, NO is also involved in the first step. And if you change the concentration of NO, BR's concentration would also be affected. And if BR's concentration is affected, then the slow step is going to be affected once more. So that's where the square relationship is coming from. Because if you change the concentration of NO, you're not just changing the concentration of NO, you're also indirectly changing the concentration of BR as well, because BR is dependent on NO. So in that way, two of the reactants, their concentration changes and the rate of the reaction is going to be affected. There's going to be a square relationship. It's going to be affected. Like if you double the concentration of NO, the reaction speeds up, the collision double. If you double the concentration of NO, BR also doubles. So the concentration of BR also doubles and the rate doubles again. So that's why by altering the concentration of NO, you affect the reaction in two ways. Is this clear? Adam, is this clear? Baki, everyone rest. Is this clear? Zoha, is this clear?
Yes, sir.
Yes, sir.
So what about BR2? BR2 is order 1. Now BR2 doesn't even appear in the slow step. Like, I mean, there is no BR2 in the slow step. So how is BR2 speeding up the slow step? Because if you change the BR2 concentration, you're changing, I mean, if you increase the concentration of BR2, the concentration of BR changes. Like if you double the concentration of BR2, the concentration of BR would also double. So if BR's concentration doubles, then the reaction would speed up, but it's only going to speed up once. So it's just a linear relationship. Like if you alter BR2, by altering BR2, the concentration of BR increases, and BR is only appearing once in the slow step. So that's how it's going to affect the slow step. It would speed up the reaction. As some more, I'll just find some random mechanisms, and I'm going to do a few more questions. Order and mechanism of reaction. Just 1 second. Not this. So let's see if we can find some mechanisms and we can try and practice this a bit more. So let's say this is let's talk about this reaction. Let's say I'm just going to copy this. And they've given us this flow step, right? So here's my other example. 1 second. So the bottom one is the overall reaction. And I think the top one need to, sorry. Okay, so the bottom one is the overall reaction. The top one is the slow step, right? That's step one. So they've given you step number 1 and they've given you step number 2. So we're going to assume so they've given us these two steps, 1 and 2. So yahan tak theek hai. So rate of reaction depends on the slow step. So that means rate of reaction depends on NO2 and it also depends on NO2. So that means that by default means rate is dependent on NO2 concentration and NO2 concentration. So that by default means square. So when you look at this reaction, this is the overall reaction. The rate of the reaction simply does not depend on CO. That's the other reactant. CO basically has an order of 0. Anything to the power 0 vanishes from the expression. Anything to the power 0 is 1. So CO concentration doesn't really matter in this case. So it depends on this. But what if this was not the slow step? What if the second one was the slow step? Let's assume the second one was the slow step. Then the rate would depend on these two reactants. It would depend on the concentration of NO3 and the concentration of CO. So if the second one was the slow step, then the rate would depend on the concentration of NO3 and it would depend on the concentration of CO. But then you'll realize that NO3 itself depends on other things. NO3 was made in the previous step. It depends on the concentration of NO2 and NO2. So instead of writing that rate depends on NO3, it indirectly depends on the concentration of NO2 twice. So now the rate equation is that it depends on the concentration of NO2 and that's squared. And it depends on the concentration of CO. And that one is order 1. Okay, so it depends which step is the slower step. And so now we're going to slightly move on. And we're going to talk about, but let me just also talk about the opposite scenario. Like if order is given, so order of the reactants is given. And you're being asked to figure out or find the slow step. So the reverse. I mean, right now we had the steps, the slow step, and we are finding the orders. Now, let's try and do the opposite. Just one example of doing the opposite. So let's say I'm running out of mechanism. Let's say I have this mechanism like H2 and Cl2 are reacting. I'm just going to make a random mechanism. So H2 and Cl2 are reacting. So what happens is they have a step 1. H2 reacts with Cl2 and it ends up forming okay, there must be a mechanism for this. Just 1 second. H2. Let me just pick one mechanism. I did open up if I can figure out or see other mechanisms. So this one, let's pick this one. It's actually the same one. Let's pick this one. So I think that's the mechanism of the reaction. So Okay, let's write the equation first. That's the overall reaction. Okay, let's 1 second. So that's the overall reaction. And this over here is the mechanism. So we've got 2 steps. Now let's say they told us, and you forget K, ignore K, there's no K, just assume there's no K. I said, now let's say they gave us the rate equation. They told us that rate is dependent on ICL concentration. I think that's ICL. ICL's concentration, and the order is 2. And rate depends on H2 concentration, and the power is 1. So let's assume that they gave us this. That rate depends. Remember, the overall reaction, the coefficients don't matter. They don't really matter. So we got the orders, and we have to figure out of the 2 steps, which one is the slow step. So we're just going to do trial and error. And we're going to see which one would give you this order. So let's figure out that the first one is the slow step. So if I assume that the first one is the slow step, then the rate depends on ICL concentration and H2 concentration. So I'm just going to do trial and error if step 1 is our slow step. So that means rate is dependent on ICL and H2. That's it. So we're getting a different, if step 1 is the slow, then we're getting a different expression compared to this. So that means step 1 must not be the slow step. That must be not, that is probably not the right, that is probably not the right option. So we're going to cut that out, and we're going to assume now that what if the step number 2 is the slow step? Then what's going to happen? Then rate depends on HI and ICL. So rate depends on HI concentration and ICL concentration, but this HI thing is actually made in the previous step. And the concentration of HI is dependent on the concentration of H2 and ICL. So instead of a rate depending on HI concentration, it actually indirectly depends on the concentration of H2 and ICL. So you're going to add in H2 or replace HI by H2 and ICL, because rate is indirectly dependent on, it's indirectly dependent on these two, because HI is dependent on these two. So in this way, if I sum this up, rate is dependent on H2 concentration, and that's only once, and ICL concentration, that's twice. So you're getting the same expression. So that means the second step is the slow step. So that's the second type of question that you're going to get, that the order of the reaction would be provided to you, and you'll just do trial and error. Just assume the first step being the slow step, second step being the slow step. Whichever step gives you the right orders, that's the one that's the slow step. Okay? Is this clear?
Yes, sir.
Okay, Lubena, is this clear? Shafak, is this clear?
Yes, sir.
So, now moving on. Okay, now let's move to the next thing. That's all about mechanisms. Let's move to the next thing. That's there's a thing called, there's another way of finding orders. Okay, that's the second method. And the second method for finding order is, that's known as a half-life method. So the half-life method is that I've got 2 reactants. I've got A reacting with B, and it's producing C. So as the reaction proceeds, the concentration of A and the concentration of B are both going to change, right? And they would probably decrease. I mean, whenever most reactions happen, both reactant concentrations would decrease. And when they decrease, the reactions, they always slow down. They become slower and slower. Like you're burning something, it eventually slows down. Most reactions, like you pour Coke into a glass of water and their bubbles produce initially and then they die off, they slow down. So reactions, they slow down because the reactants get used up. So the first problem that you're going to face is that if I want to figure out the order with respect to A, then B would also be interfering with it. Like B's concentration is also changing, right? So somehow what I need to see is I need to see the effect of A independently. And I want to see how the reaction would be affected if I alter the concentration of A. If the concentration of A goes up, if it goes down, how does the rate of the reaction change? I want B to be constant. So how can I keep this in constant? The only way I can keep B constant in a reaction is that if I add it in large excess. So B's concentration would in effect be constant. For example, if I have 0.5 moles of this and I've got 100 moles of B. So no matter how much the reaction happens, like A's concentration drops to 50%, it gets used up. If it gets even completely used up, the moles of B would hardly change. Like 0.5 would only react with 0.5. So that means out of the 100 moles, 99.5 moles would still be left. So even when the reaction proceeds, the amount of B barely changes. There's barely a noticeable change. So that means when something is in large excess, its concentration kind of becomes constant. Is this point clear? Ethan, Mohammed, is this clear? Ruba, is this clear? Zoha?
Yes.
Yes.
Okay, so that's the first thing. Like, I want to figure out how the rate would be affected by A. Is it directly proportional? Is it going to be affected at all? Like if it's zero order, I change the concentration, nothing happens, right? Or if I change the concentration, if I double the concentration, the reaction becomes 4 times. It speeds up by a lot. So I'm investigating this. So the first thing is I need to get rid of B. And I want its concentration to not change. So now there's 3 ways. So now what I've done is I've sort of made A independent of B because B is not changing. So the rate of the reaction is now only dependent on A, like what's happening to it. Because nothing is happening to B. B is almost constant. So the rate is not going to be affected by B. It will only be affected by A. So we are now trying to figure out like previously it was dependent on both things, but I've kind of made B constant. So rate is no longer dependent on B. So I want to figure out what's the order. What's the power A? Is it 0? Is it 1? Is it 2? So what I do is I plot a graph of how the concentration of A changes with respect to time. So on one axis, there is time, and on the other axis, there is A's concentration. Now, as the reaction happens, if it's a 0 order reaction, the graph would look like this. Like if the rate of the reaction is A's concentration to the power 0. I mean, that means, remember, A is going to react and eventually get used up. So initially, A concentration would be very high. And then when the reaction happens, it slowly goes down and goes to 0 with respect to time. So A is going to get used up. What this graph tells you is that as the concentration of A decreases, nothing happens to the speed of the reaction. It's a straight line. The gradient represents the speed. Like how fast is the concentration decreases. So gradient is proportional to rate. Is the reaction slowing down? Is it taking a longer time? Is it speeding up? So over here, the speed with which A's concentration decreases, that's constant. It's decreasing at constant speed. It's not slowing down. Like over here, it should slow down. It should take a longer time. Like it should, like if A concentration decreases, if it was dependent, the rate of the reaction should slow down, but it's not slowing down. So that means rate is not affected by A's concentration. As A's concentration decreases, drops, the reaction, the speed with which it's decreasing, it remains constant. Is this graph clear?
Yes, sir.
Yes.
Okay, so Lubena, is this clear? Adam, is this clear?
Yes, sir.
So the point is, reaction starts, A's concentration starts to decrease, it gets used up, it gets converted to C. A's concentration starts to decrease, eventually goes to 0. The reaction doesn't slow down. It just happens at a constant rate. Now the second graph, what if rate is dependent on A's concentration? So in that case, if rate is dependent on A's concentration, then that means the reaction with respect to time should slow down. So what I'm going to do is I'm going to make some lines first, and I'm going to explain those lines later on. So this, just a second. Okay, let me make these boxes just. Here, all these boxes have a fixed length. And one more. So I think that's enough. And our starting concentration is over here. This is the second point. This is the third point. This over here is the fourth point. This is the fifth point. So I just need to draw a line now. This is showing how, if it's order 1, the reaction, it continuously slows down. I mean, it's going to take a longer and a longer time. As A's concentration drops, the reaction kind of slows down. I mean, it's taking a longer and longer time. This is what happens. Like if you put Pepsi in a glass of water, what happens? Initially, the bubbles are produced a lot. Like it's very steep. In a small time, a lot of bubbles are produced. And then it takes a longer and longer time. The production of bubbles slows down. So it just takes more and more time now. So A's concentration, as the reaction happens, where's the reaction? Initially, the concentration is really high. So that means the reaction is really, really fast. So initially, the reaction, in a very small amount of time, A drops very quickly. But as A's concentration decreases, the rate of the reaction slows down. It takes a longer time. It decreases even more. The time required keeps on extending. So it forms an asymptote. So this is order 1. Is this clear, the graph?
Yes, sir.
This is order 1. Order 1 means rate is dependent on A's concentration. So as the reaction proceeds and A's concentration drops, I mean, it gets used up, it decreases, and the reaction would slow down. So it's going to take a longer and longer time for A to decrease. I mean, initially the concentration is really high. The reaction happens very quickly. Then the concentration starts to decrease, the reaction slows down. The gradient becomes less steep. And it's never going to touch the bottom axis, the x-axis. That's never going to happen. ठीक है, is this clear? Adam, Ethan, is this clear? Lubena, Shafaq, is this clear?
Yes, sir.
So this is order 1. And so how do you figure out what's the difference between order 0 and order 1? I mean, you just have to plot this graph, and you'll by just looking at the graph, you'll figure out what order 1 and 0 is. We talked about half-life. I'll just tell you what the half-life is. That's why I was drawing these boxes. Half-life is the time for the reaction concentration to decrease by half. So your concentration was over here, now it's over here. The second half-life is the concentration of the reactant to decrease by half again. So it decreases by half again. So that's your second half-life, that's T2. The third half-life is the concentration to decrease by half again. So that's T3. The fourth half-life is the concentration to decrease by half again. That's T4. Now in a first order reaction, the half-lives are constant. Is this clear as well?
Yes, sir.
So the half-lives are constant. So if there's a graph that's already plotted for you, they might give you data and you have to plot the graph. You can just look at the half-life, like how much time does it take for the concentration to decrease by half? And then how much time is required for the concentration to decrease by half again? And then again. So if the half-lives are constant, that's automatically order 1. That means the reaction is slowing down. That means the rate is dependent on the concentration of A. And in order 0 is clearly, I mean, you don't even have to calculate the half-life for order 0 because it's a straight line. You get a straight line. But if you were to measure the half-life would kind of look like this. Like what's the time needed for the concentration to decrease by half? That's this. Then what's the time required for the concentration to decrease by half again? So that's this. What's the time required for the concentration to decrease by half again? That's this. Now you can see that every time the half-life or the time needed kind of decreases. Like the first half-life is big. The second time it's smaller. The third one is even smaller. So in this case, each half-life is half of the previous half-life. Half of the previous half-life. So is this clear? Concentration was here, decreases to this by in this much time and decreases again to this by this much time. So every time the half-life is becoming lesser and lesser. So is this clear to everyone?
Yes, sir.
Okay. Then here, let's continue tomorrow. But tomorrow you'll have a quiz on equilibria. Okay. I'll if you need any help, any video lecture, I'll send you those lectures. But there's going to be a quiz on equilibria. Okay. So we'll do that. So that's the second method. We just have one more to go. That's order 2. I didn't tell you about order 2. We'll do that in the next class as well. Okay, everyone. Let's
Thank you.
take care. Allah Hafiz.
Thank you.